Everyone, we're going to be working on part 3 now. So just as a quick summary of what we've done. So the first thing we did was we made equations 1 and 2 into a 4-dimensional first order system by introducing our variable y and dy dt. Now for part 2, we introduced an event function that allows us to determine when the end of the first step was. Now what we did after was to plot the first step only. Now what we're going to do is we're going to create the second step, and to do the second step we need the initial conditions for that second step, which are going to be all the end conditions of the first step. And in order to do that, we're going to use equation 5 here. What equation 5 allows us to do is take all of the initial values of y, so this is y1, y2, y3, and y4, for the first step, and then convert them into the initial conditions for the second step by multiplying it times this matrix here. What this means physically is when you're walking, your first leg is a pivot and your second leg is a swing. Now on your second step, the leg that was swinging becomes the pivoting leg, and the leg that was the pivot becomes the swinging leg, which means that the angles theta and phi are going to switch around. And that is what we're going to be doing with this matrix here. The first thing that we're going to do is we're going to introduce the y minus. Y minus is going to save all of what we had at the end of the first step. Now, in order to teach you how to do this, we're going to go back to our example. Let's assume we have a matrix that looks like this. Now, if this was our matrix that we were looking at, we would have y1, y2, and y3 here, for example. What we want right now is the last time. So if this is y1, y2, and y3, these are time 1, time 2, and time 3. In this case, time 3 is the end time. So what we want is to get all of the final conditions of y, basically y1, y2, y3, y4, y5 for t equals the end. Before, when we used to have a vector for t, for example 1, 2, 3, 4, 5, if we wanted the last time, we just said t end, and that gave us 5, correct? Now what we want is the whole set of the last values. To do that, we're going to use y. We're going to tell it give me all of the we're going to tell it give me the end of all of the columns. And what that's going to do is it's going to take the last row, but all of the columns. Now, when we do initial conditions, we need a column vector instead of a row vector. So we're going to convert this into a column by doing the same expression, so y end comma colon, but then to put in an apostrophe to get the transpose. So we want a column vector to make our initial conditions, and that is what we're going to do. We're going to create a y minus, which is going to be this vector here in your fifth equation. And you see it's a column vector, which is going to be this equation here, y end comma colon, okay? And then your apostrophe, so it's actually this one here. Now when you're created that, what you're going to do after is we're going to create this c value. So the c value, what it is cosine 2 theta. What this parenthesis is not that it's multiplying. It means theta add t minus. So it's just your last theta. So in order to, what is theta? Theta is y1. So basically it's just y1 or y minus 1. So what we're going to do is c is going to be equal to the cosine of 2 times and then y minus, and we want the first value because our first column of y is theta, our second column is phi, our third column is theta prime, and our fourth column is phi prime. But we want theta because it's cosine 2 theta, so we want a cosine 2 times y minus 1 times y minus, 1. Now that makes our c value here, which is this expression here. Now you have to make the matrix. To make the matrix, remember that between columns you use a semicolon, so it would be minus 1, 0, 0, 0, then a semicolon, and then the next line, and then the next, and the next, and the next, until you have a 4 by 4 matrix. Now in order to create tau plus, we just have to multiply this matrix we've created times our y minus. This vector here again is y minus. So our y plus it is going to be a times y minus. And it's important that you do it the right order and that you don't add a period here. And the reason is that this is a matrix vector multiplication. We don't want a period, because if we add a period, then we're going to have element-wise multiplication, and we want it to be in order because this is non-commutative matrix multiplication. You can leave it out because I think they want you to output y plus. I'm not certain, but I think you can leave it without a semicolon. Now, the next thing you do is you run your ODE the same way. So we can go ahead and copy and paste the same ODE here. However, you have to adjust your two conditions here. So first of all, the first step began at 0, but now our second step begins at tau. So you need to add tau to each one of your boundaries. So we want the first step to begin at the end. We want the second step to begin at the end of the first step, which is at tau. So you're going to add tau to that first one, and of course you're going to add tau again to your second one as well. So this what this is doing is, in terms of time, it goes ahead and it runs the first step, and the second step begins at tau. It doesn't begin at 0 anymore. Now, y naught is not going to be y naught anymore. Y naught now is going to be y minus, because what we're doing is we're taking the initial conditions for our second step are the end conditions. The initial conditions for our second step are the end conditions of our first step. And that's why our initial conditions are now going to be y minus, and that's why we put them in terms of a column vector. Now, the second thing that they ask you is to find our second tau. Basically, the end time of that second step. And to do that, what we had done initially was to create a tau, a variable in this part here. So now we're going to do the same thing. We're just going to create a tau. We can give it number of 2 so that we can keep on saving them, or we can just call it tau2. And that is just going to be, again, the end of the time. We already know how to find the last time of that ODE function. Sorry, here I messed up. So we're just going to get the last value of time for tau2, and that's going to be the end of our second step. Now you can go ahead and plot the same way you plotted part 3 and add the same labels, and then you should get a graph that is very similar to the graph of part 2, but it's just going to be the second step. And then to make sure that your time limits are right, it should begin at about 3.7, which was the end of your previous step. That's when it should begin, and then it should end at about 7.6, your graph. If you did it right, these are your two limits. That's all you have to do for part 3.